Okie doke.
All right, you are up and running, and I'll let you take over in just a second. Everyone who's here, welcome. This is a fairly long laboratory, and example 0, which Josh is about to start to go through, is going to be important to you because you'll get to see it again on exam 3. And the remaining examples in the lab are practical application of the ideas of hypothesis testing. So they're meant to be read through in detail and then played with. Jose, the way to get to the lab is to go through the syllabus because the syllabus links are good, and that will get you to the lab. It's there.
Okay. So today we're going to be talking about hypothesis testing. And as far as a practical understanding of statistics goes, this is probably the most useful thing I think you can pick up from it. And I'm talking in a general sense, not just in a data science sense. What it does, the real thing it lets you do is when you're told a claim, especially one that you're like, wow, that's surprising, I wouldn't have guessed that. And they say, yeah, here's my sources. You can now tell, in a lot of cases, you can now tell what method they used and if the data actually backs up what they're talking about. And that's really important. So let us consider an example to see, and we're going to run a hypothesis test on this. And what do we do with a hypothesis test? Remember that, I guess I can just look here instead of having to draw it. What does a hypothesis test let us do? It lets us either reject or fail to reject the null hypothesis. And whatever the null hypothesis is up to us. But we now have there was a diagram, yeah, here. We now have a way of, within the tolerance we set, correctly rejecting or failing to reject our hypothesis. Now, as far as standard numbers of significance go, I've seen 95 and 99 a lot. Of course, the further you go, the more powerful you get. It gets exponentially harder to test. So 100% is not possible, and the closer you get to it, the harder it gets. So let's get right on with our example here. So first thing we want to do is we want to make a data frame out of a CSV file. Now, in my office hours, actually, I believe, anyway, it's not important. During my office hours, I had a lot of questions on manipulating some of these things. And I found that some of the students who were asking were having trouble assigning a type in your mind. What kind of thing is going on here? It's important to note that what kind of thing does Pandas give us that we use most of the time? Well, it's a data frame. Data frames are the real power that Pandas lets us get. So what do we have going on here? We have a CSV file somewhere. There's a link here, but I've been using the web root. So that's linked here. We have a CSV file. And what does that mean? It means the file extension for this, I have it right here, for this data is .csv. Now, if I don't set this to comma, you'll see that it's just a bunch of numbers separated by commas. It's what a CSV is. It's the right kind of file. And what are we going to do with it? We're going to make a data frame out of it. So Let's call the essentially CSV to DataFrame function. It's called read underscore CSV. Comes from pandas. And we're going to get the first and last 5 rows of our data frame. Now, another thing that I found helpful to remind the students in office hours was that remember that the columns in a data frame, they have a type. They're a thing we've worked with before. They're called a series. Okay, so we've got our data frame. Nothing fancy going on, didn't have to change anything. Let's check out what our data sets look like. So, as I was just saying, each column in my data frame is a series. So I've got my first column, set 1, my second column, set 2. My data frame is called data, and I can access, this is one of the powerful things about a data frame, so I can access the entire column instead of having to say column 0 or column 1, I can use the column name. So I'm going to put a series in set 1, this is a variable, and a series in set 2, and then I'm going to print them out. Now we're using, there's the built-in functionality that when you print out a series, it'll give you the first 5 and the last 5 because we don't want all 100. We could change that. I forget the exact argument, but we could print the entire thing out if we wanted to. Usually don't. All right, so what are we looking at? Well, we've got 100 float elements. We can see they're in the 40-ish, 60 range. Now, if we remember, last week, we talked about some descriptive functions like mean and mode and median, stuff like that. But one thing we have that lets us look at a bunch of those is the describe. So let's describe our set 1, which is the first column, and describe our set 2. So there's 100 of them. The mean is 48.5. Standard deviation of 15.8. The smallest one is 13.6. And we have our quartiles and the maximum. So all those descriptors we were talking about, you can have a good selection of them in a nice package. We can do the same thing with set 2. So what can we say about the difference between these two? Well, set 2 has a higher standard deviation than set 1. Additionally, the actual values are higher than in set 1. They're both floats though. This box here, I had to change. I was getting an error for reasons I'm not sure, because it looked like this to start with, and I had to change it to giving it the moniker PLT. I don't know why, but when I did this, it would actually work. So what does this let us do? Well, it gives us a histogram of both sets, and we're going to show the plot. It shows where the values for our set 1 are falling and the values for set 2. Now, what do the numbers on the left mean here? Well, this shows us for a value of 0. I did finally figure out how to get this drawing hotkey to work. For a value of 0, we have an occurrence of 0. For a value of, what did we say? Okay, so let's say 49.3, which is probably right about here. What's the occurrence? So 49 is right here. What's the occurrence? 16-ish. We could look up the mode to actually find out what the one on the right here is. But this is how you read this chart here. Now we get into what we actually want to do. We want to test to determine if these two sets of data are the same or if they're different. Now, after reviewing lesson 16, we have a bunch of tests here. Some important tests, and they have scripts to go along with it. So the task here is we've got some data. We want to use hypothesis tests to see if they're the same or different. So we've got 1, 2, and 3 things I'd like to do. The first one, I want to test if each sample appears normal. So I need you guys to tell me which of these tests we have here and shall we use. And it's going to be pretty simple because we can copy and paste, but the question is, which test do we use? So you can feel free to scroll yourself. You can tell me where to scroll, but I need someone to tell me which test, and you can just give me the name, do we need to use for our test. And remember, we're trying to test if each sample appears normal. So which one should we use? Does anyone have an idea? Now these tests have descriptions of what they do. So I need the one that talks about testing if something is normal or not.
The
And there could be,
hypothesis,
which one?
hypothesis test.
Yeah, they're all hypothesis tests. So someone says Shapiro-Wilk. Let's take a look for that one. I believe it's up here. Yeah, it's right here. So this one says, tests whether a data sample has a Gaussian distribution. So observations at each sample are independent. Okay, we already know, we're assuming that. And then the null hypothesis will be a sample has a Gaussian distribution. And the alternative hypothesis is that it does not have a Gaussian distribution. So we were talking about normal distributions. So can somebody tell me why the test is talking about a Gaussian distribution? What's the difference in a normal distribution and a Gaussian distribution? Yeah, they're the same. Good job. All right, so this test, sure, why not? I don't see any reason not to use it. So I believe there are a couple, I'm sure almost every package has something. I believe this will work with a series. If not, we'll work around it. So since we're just working with copying and pasting, the hard part was figuring out which test to use. Let us do this. All right. So let's do this one at a time. Our first piece of data is set 1. Let's see, do I need to change anything else? I don't think so. Okay. So we can look back and forth, but can somebody tell me how to interpret what the output is, specifically this part? What do these mean? I don't know very much. All I see is it's a variable name called stat and a variable name called p. Well, what do these mean? What does a stat of 0.992 mean? Well, if we don't know, we can go look. What does a hypothesis test let us do? Okay. Remember, that the p-value is what the it's the second argument. It's the point at which if the value we see is on the left, we do not reject the null hypothesis. If it's on the right, we do. The other argument we have, we're talking about the level of significance. So what did this tell us? Well, the value was to the left of our test level of what I'm assuming is 0.5. Let's look. Yeah, here it is. Yeah, so we failed to reject. And what was our null hypothesis? Is that it's probably Gaussian. All right, so that's the first one. Let's try the second one. Let me do that again. And yeah, we'll get to that in a second. Set 2. Let's see. All right. So we have both of our tests, I'm sorry, both of our sets being tested, and they're not really sets, it's just what they're being called. And oh yeah, here it is. Here's our value. So this is the p-value, and we're comparing it to 0.05. So we're looking for our 95%. So when we tested this using our, what I'll call Shapiro test, I can't remember the other person's name because it's not listed here. What we got was 0.793, and what we were comparing against is 0.05. So our code does exactly what we would expect if we're doing a conditional block here, if something is less than something. And the real part that is going on behind the scenes is here. But we have tested our two data collections. I hesitate to use the word set because we didn't say it was a set, but you could store it as a set. So I'll say set from here on. We've tested our two data sets for normality, and according to the Shapiro test, which we selected, they both appear to be Gaussian. Now, they could always not be Gaussian. They could always not be normal. As I said, part of the difficulty is choosing the right test because there's just so many of them. Maybe we chose a bad one, maybe not. But I don't see any evidence that would say, nothing surprised me that these kind of look normalish, and I don't think we chose a bad test. So until we have evidence that we chose a bad test, we can consider that pretty good. All right. Next thing we want to test is choose a test to see if the central tendency is the same. So we have a bunch of stuff here. Which test should I get to copy and paste for central tendency? Does anybody have an idea? So what does this one do? Test whether the means of two independent samples are significantly different. Okay. Test whether data sample has a Gaussian distribution. Okay, we kind of just did that. Test whether has a Gaussian distribution. Pretty good to know. You can have a, you kind of have them listed here. So if we're talking about central tendency, what does that mean? Does that mean Gaussian or normal? Does it mean comparing the means? Because that's what these two are. One's parametric and one's not. So which category would be an appropriate selection for talking about the central tendency? It is comparing means. Yes, that is correct. Why is comparing means talking about central tendency? Well, think about it. You got your plot. What can the central tendency look like visually? It's where the center tends to be. So if and this will be the mean. doesn't mean that it's the most, it doesn't mean that it's the mode, but a lot of times they're very close. But usually the 50th percentile is going to be close to the mean. So where does this lie on the graph? Well, central tendency means could be here or could be here. Talks about where the mean is horizontally. Okay, so we're going to use a sample means, and we're going to use a parametric one first. So which ones of these should we use? I don't particularly care, whichever one you guys like. Okay, t-test, we can do that. Gotta look up which one that actually is. Okay, there's two, so let's just do the first student's t-test. I believe we already assumed that these are independent samples. Let's see if it's actually explained. All right, we don't know a whole lot about the data, but we already assumed that they were independent to use the Shapiro test. So let us run with that assumption. So if we're assuming they are, oops, this is the one I'm looking at. All right. Copy and paste. Okie doke. We don't need this. Don't need this. Set 1. Set 2. Okay. Unless I messed something up. Okay. Wow. We got a big outlier on that one. So according to the student's t-test, which tests whether the means of two independent samples are significantly different, we reject the null hypothesis that they are probably the same, that they have a central tendency that's close. Just for the heck of it, I'm going to get this one too. So one of these is for paired data sets, and one of them is for non-paired. And I just want to see the difference. All right, set 1, set 2. Okay. So in both cases, we're seeing that they are probably a different distribution. We're setting our p-value to, we want 95%, meaning that if we get something less than 0.5% and 0.0 is less than 0.05, then we're going to reject the null. And what was the null? The null was to see if the central tendency is the same. And this kind of lines up with what you would visually a little bit expect. The mean doesn't seem to line up. Let's see what would happen if I run the test on the same data set. Well, we almost get exactly the opposite. The test is telling us that the same data set is probably the same data set. So not entirely unexpected. Okay, now let's do the same thing with a non-parametric test. So someone pick a non-parametric test that they like, and we'll do that. So one of these. Really? Did I get a syntax wrong? Set 1, set 2. So Dylan's saying that he's getting that they're the same. Obviously, it's hard to see your syntax errors, but I believe I have it set up correctly. So if someone sees an error, please let me know. In the meantime, let's work with a non-parametric test. Does anybody know what's the difference between parametric and non-parametric? What does it mean to be parametric? Does anybody know? I think that sound means someone's joining. I thought it was a chat for a second. Let's take a look at our non-parametric tests and see which one we like. I think this is the first one. Oh, so I asked, what is the difference between a parametric test and a non-parametric test? Because we lose power when we switch from parametric to non-parametric. So if I were asked that question and I didn't know, I'd probably look at lesson 16 or maybe one previous 15, and I would control F parametric to see where it's defined. That is, yeah, that's pretty close. That's pretty good. That non-parametric doesn't depend on the distribution. That, yeah, okay. So when you're selecting a test, we're looking at a non-parametric one right now. Kind of what you want to look at is consider your data set or data sets and look at the assumptions. Which one best fits what you're talking about, and then go from there. So the Wilcoxon is more what is the word? Has more strict assumptions. So I'm going to use a more general one. I'm just going to pick this one because it's here. Let's use this one. Okie doke. Don't need this. Now I'm going to do what I did before. If it says that the same set isn't the same distribution, then we're in trouble. Well, it says that the same set is the same distribution. So we at least know it's doing something sensical. Now, when we run the Mann-Whitney test on our two sets using a p-value of 0.05, we get that they are probably different distributions, which lines up with what we were looking at with our parametric tests. Okay. Now we can always look at some more stuff, run some more tests on different things. We could change the p-value. Sure, let's do that, see what it does. I'm going to set this for 0.01. And if my computer dies, we all know why. All right. Nothing changed. Not unexpected because the value we're getting is this. Now, I wonder, I know there's a way to do it, but I can't remember the top of my head. What I'm thinking of doing would be I'm going to take, I don't know, set 2. And I'm going to subtract 5 from every element in the set. And then I'm going to compare that against itself. So I'd have set 2, which is set 2, and then set 3, which is set 2 shifted just a teeny tiny bit. But since I didn't have that prepared, I just now thought of it. If for some reason we get through everything, I'll look up the syntax for that. Because I don't want to, I could write a for loop to do it, but I know there's a method that lets you do that to every element. Okay, so that's example 0. Any questions? I'll summarize what we did. And while I do that, feel free to put questions in chat. We had a CSV, 2 CSVs actually, or I'm sorry, just one. We had a CSV with 2 columns. We wanted to make a data frame out of it because a lot of our tests run data frames really well. So we imported We use pandas to get our data frame. We separate out the columns. And then we make a histogram so we can visually see what's going on here. And then we run some tests. We use the Shapiro test to see if the samples appeared normal. And then we wanted to see how these two sets lined up with each other. See if their central tendency is the same. We used a parametric test. And then we used a non-parametric test to see, well, they actually used two parametric tests to see if our distributions, which are visibly different, were similar enough to be considered the same. And to no one's big surprise, with a p-value of 0, the null hypothesis was rejected. Now, keep in mind, the data sets we're looking at, you can almost visually answer most of these. But if I were to give you kind of like what I was just talking about, if I give you a data set that kind of looks like this, tails off to the right a little bit more. So this one I just made compared with the data set 2. Not as easy to visually say, are they the same or not? Depends on your p-value. So what I'm getting at here is if your data sets change, don't think you can just answer the same way we just did. All right, let's look at example 1. Do construction activities impact stormwater solidness metrics? Let me see, I gotta move my camera thingy. Okay. So, some background here. The Clean Water Act prohibits stormwater discharge from construction sites that disturb 5 or more acres unless authorized by by permit. The permittees must provide a site description, identify sources, appropriate measures they're taking to reduce pollutants, and implement those. I don't think I need to read all this. Basically, the point is, here's the important part. When you're doing work that disturbs soil or buildings, anything that could, when it rains, there's going to be a whole bunch, especially if there's like, let's say you're busting up asbestos or something. You can't just leave that powder around everywhere. If it rains, it gets into the storm system, the stormwater system, and a lot of cities recycle that. And as we all know, that sometimes, consider mercury, for example, that's a material that it can't really be filtered out of the food we eat. So if your stormwater filtering system can't handle whatever could be on a work site, that means it's going to be in the water you're using. So we're saying that the workers need to put in a system that makes their the amount of solids in stormwater be below a certain threshold. So we've got some data on that. We've got the solids before some work and some solids during some work. They contain observations of cumulative rainfall, total solids, and total suspended solids collected from a construction site on this is a real data. The pretext was collected before construction began, and during was collected during. First few lines look like this. First column is the date. Second column is total solids. Third column is the total suspended solids. And the last column is the cumulative rainfall for that storm. So what you could consider is when I go and I talk to the supervisor, the real bottom dollar is going to be, look, if there's an inch of rain, this is the amount of solids that you can increase the background level of solids. Like there's going to be solids in the stormwater depending on where you live in the world due to soil, all kinds of factors. I mean, tree pollen could be considered solid. But take whatever it is per, let's say per tenth of an inch is what we're going to be standard measuring by. The background level when there's no construction going on is X. You can increase X by 10%. If you go over that, you're in trouble. So what we have here is the background knowledge or the background levels. This is before construction, and this is during. So our task is to analyze these two data sets and decide if construction activities impact stormwater quality in terms of solids measures. So as we go on, let's keep these questions in mind. Which summary statistics are relevant? Are the data approximately normal? Are the data, I've never been able to pronounce this word, homoscedastic? Do the two data construction phases represent approximately the same rainfall conditions? Assuming the observations are upstream of any water quality control feature, what amount of solids load needs to be captured to preserve pre-construction loading to the environment? So this last one means, let's assume you're upstream from everybody's drinking water. Now, cities usually do at least some level of purification. We're not drinking straight from the lake, but that purification isn't perfect. So if the quality feature, let's say if the parts per million, and obviously I don't think we have that measurement, but let's just say parts per million for now is over 500, then it won't work. So then we have to ask ourselves, need to purify the level of water more. I've never liked the water here. If you've ever had well water, the water here is not very good. I always have purified water or bottled water. But yeah, I agree. Maybe there's too much construction going on here. Okay. The data are not time series. There was sufficient time between site visits that you can safely assume each storm was independent. Meaning, well, let me ask you guys. What's a situation? Think about situation in the climate. What's a situation where it wouldn't be fair on the workers if my two data sets came from, what's something weird that could happen that could make it to where I could choose the time to go and it be not fair to them? What I'm getting at is, what is a time where we cannot assume that each storm was independent? So as you guys think of that, this is one of the reasons being able to have a basic understanding statistics is extremely important. Because let's say we all live in a small town. It's just us and our water, and I, being the investigator who gets paid whenever there is an issue. Well, I get paid regardless, but I keep my job because there's an issue, and I go ahead and report it. Well, I come to you and I'm ringing the alarm bell saying, look, they've completely put too much stuff in our water. What are we going to do? We need to fine these guys millions and millions. Well, if I'm sneaky, I can make that almost a guarantee. What's a way I could be sneaky about it? What's a way I could make this assumption not a valid assumption? And this isn't, let's see, adding more water. No, that would work, but that's too overt. Because somebody will say, hey, I saw you adding water to it. Or look, it says in your methods you add a water to it. No, what I'm thinking is the only thing I can do is choose when to go sample. So the simple thing to do is wait for a hurricane. Obviously, when is a hurricane going to hit us? But what I'm getting at is if I want to get these guys in trouble, I go and I measure beforehand during a dry spell. There's not much water, so there's not much parts in it. And then I wait for a wet season during their construction, during a big series of storms. And now the situations aren't the same, and I can take advantage of that. And I don't even have to disclose that. I don't have to. You have to go look for it. So this assumption here that they're independent is a big one, is the point I'm trying to get across. If the person collecting the data intentionally waited for the conditions to support whatever conclusion they want, that happens all the time. Turn on the news right now, and I'll find at least one. But that was a good guess. All right, first thing we need to do is get our data. So this time, instead of me actually downloading these and putting them in here, we've got some commands to do that. We're going to use the get from our requests package. Now, this line here was originally this, LSLA. Now this is for Unix. And the equivalent command for Windows is dir. But when I put these in the same cell, it wasn't having it. So I moved my dir to the next cell. If you're not running Windows, just keep it as ls-la. And for some reason, I do get a number back. I'm assuming it's some kind of success message saying that, yeah, everything worked. So I run this and I get this number. I'm not sure why. Maybe it's the number of lines in the file. Don't know. But what are we doing? Well, if you look here, there are 3 lines. Same thing here. So the first thing we do is we're going to set a string that's going to say where our location of our stuff is. And then we're going to say, I want my file name here, and then use get to get it and open it and write it to a file. And then the same 3 lines here. So we're going to get both of our data sets. First one is before, and the second one is during. So now we have those written into text files. Here we go. And then we see I run dir. Now keep in mind, I have all the labs here. So it looks like a bunch of stuff, but we can see that solids during and solids pre are there. We see the size. I think ls-la only gives the name of the file. It's just there to see that we have it. So I don't think these numbers would show up, but it is interesting to note that one is much bigger. Okay. Let's examine the files and see if we can understand their structure. Now, just as we had a, I believe it's read CSV. Yeah, read CSV is a method that Pandas gives us. We have read table, which will work on text file. So what are we going to do? Well, we're going to import Pandas. And then we're going to use the, essentially, you can consider this to be I would consider it to be txt to DataFrame is kind of what your function is. It's a text file, converts to a data frame. It is called read table. And then we're going to do a box plot. Okay, so this is the beforehand measurements. Now, what were our column? I'm going to get rid of this. Clear that. What were our column values? Let's see. We got the total rainfall. We've got the total solids, and then the total suspended solids. Now, what's the difference between total solids and total suspended solids? It's been a long time since geology, but my base level of knowledge is telling me that if I collect water from the storms, so if I take a big old ladle and collect some storm water, well, there's going to be dirt at the bottom or solids that just settle at the bottom, and there's going to be some solids that don't settle. So if consider my beaker, I'm going to take my beaker here and I'm going to fill it up with stormwater. There is a total amount of solids in the beaker itself, but those solids can be categorized in two ways. There is the stuff that settles to the bottom, and there's the stuff that stays suspended in the water. So that's what it means by total suspended solids. So yeah. All right. So the total solids, we can see an outlier here, another outlier here. And we can see our quartiles and all this stuff we talked about with the box plot last time. So we see a range. I'm not sure the actual units. Could be parts per million. Don't know. Doesn't particularly matter. We could call them squibbles. Doesn't matter. It's a unit. If I go to the forum and then I say these are the range of squibbles you can have, and what kind of unit is a squibble? Well, it's a particular amount of mass of solids per volume of water. So we've got our window of what it looked like. We got an outlier. We have our suspended solids, the window of what it looks like, an outlier here, and we have the amount of rainfall. Now, unfortunately, the data on these two is so much that it's kind of hard to see. It looks like just a flat line. But if we look at the pre, it's unfortunate that it's aligned this way. This is, how best to say this? This is no small amount of water. I mean, and this is an inch in a storm. It's a day's worth of rain, and that's an inch. It's a lot. What I could do, I think, is I'm gonna duplicate this, and I'm gonna say, oh man, that would be a giant pain. What I was gonna try to do was delete these two columns, but I can do that with code. I'm not entirely sure it's worth it, because the only point I'm trying to get across is that it's because these two things are measured in the hundreds that this looks like nothing, but it's not nothing, because as we all know, an inch of rain, especially here, that's a lot of rain. What we can do, pandas remove column from data frame. Okay, drop should work. Yeah. That's what we want to do. I didn't know the plot would actually run the series. I guess we already did that though, so I should know that. Yeah, let's do that. Let's see. Rainfall, we'll call it that, is, what did we call? Put it here. Rainfall is pre-con, and what was the name of the column? It was this. So what are we doing here? Well, as we did before, in example 0, I'm going to get the series out of my data frame by using the name of the column, and then I'm just going to plot it, just as we did here. Will that work? No. We need, let's see, plot the box. We have it up here. PLT dot box should do it. Ooh. Huh. Well, what I can do is that'll work. I go. Okay. Oop, wait. Don't need this. Sorry. The amount of time spent on this isn't probably worth the point I'm trying to get across. All right. I'll come back to that if we have time. Point I'm trying to get across is that the amount of rainfall is not 0, even though it looks like a flat line. It is something we can compare with. All right, so this is the before work goes on, and this is the after. The columns are switched in order. Interesting. But that doesn't matter too much because they have the same names we need. So if we look at the total solids for during, whoa, look at the change in numbers on the left. We have a range here that is higher than the highest outlier before work started. Now, it's not entirely unexpected. If I'm making a lot of commotion and disturbing soil, of course the parts are going to go up. So the question is that outside the amount of, it's the question we were talking about here. Is it too much? How much is too much? That is the question. Now, one thing we did want to talk about is, do the two construction phases represent approximately the same rainfall conditions? This is kind of what I was talking about. If I want to go wait until there's a hurricane, I can, and that's kind of cheating. So what we can do here is I can do this. Here. And it's not as nice as a plot, but it's something. Okay, so actually I can do a describe on a series, can't I? Yeah. Yep. So instead of a print, let us do, where did we go? I lost it. Here it is. Describe. No, wait, it's a method. Dot describe. Okay. Now, I'm doing exactly what's listed here. Okay, beforehand, we had 17 measurements, a mean of 0.87 inches. The minimum was 0.13 inches, and you can see our quartiles here. Max we got was 3.7. Here, the mean was 1 inch. It was measured 37 times. The maximum was 6.5. Holy cow. That is a lot of rain in one day. And the minimum was 1/10 of an inch. I'm assuming this is in inches. Let's look at our percentile, because the maximum, I mean, just because one maximum is an outlier doesn't mean necessarily that two data sets are too dissimilar. But we can look at the quartiles and see how close those are. Obviously, we're going to be able to see that here in a second, but we can just look at the numbers. Yeah. So what Dr. Cleveland posted in the chat works just fine. I just jumped the gun and I got too excited about stuff and I didn't notice that they were actually just here. Okay. So here is the box plot for the two. And considering this is just rain, the numbers on the left should be somewhat similar. So note that the range we have here is somewhere between, let's see, for during our minimum was 0.1 and the one before, close enough. All right, so the minimum is pretty much the same, but the scope on these is a little different. So notice that this area here is the same here. So the one on the bottom is more smushed. The graph, I'm sorry, the one on the top, meaning that if we were to take the two things in the red box and look at those are the things we need to look at. So as we can see, looks like we got a lot more rain during this area, but we did measure more. How would we figure out if they're actually different? Visually, it's a little too hard to tell. It's almost like we had an entire lesson on tests we can run to see if these are too different. Let's run some of those tests. Okay. So what are we going to do? We're going to compare the rain before and the rain during, and we're going to use the one we used before, the non-parametric one, the Mann-Whitney test. We're going to use p-value of 0.05. Okay, so we're saying the null hypothesis is not rejected with a p-value of 0.05, but they are probably the same distribution. And remember, this is just measuring rain. What makes these difficult, other than the outliers, is that the number of measurements is different. And that doesn't necessarily mean that was intentional, because what they're measuring is amount of water per rain rather than how much rain did we get in the year. So if beforehand we had, what did we say? If beforehand it rained 17 times in the same period as it rained 37 times during, it just means it rained more often. Doesn't mean that every storm rained a lot more. So according to our non-parametric test, we see that the distribution, the null hypothesis is not rejected. And here, same thing. So from these two tests, and note that the data is not paired, we conclude that the two sets of data originate from the same distribution. Thus the question, do the two construction phases represent approximately the same rainfall conditions, can be safely answered yes. Now we were using a p-value for 0.05. How strict do you want to go? Well, you never really see this. 0.05 is the standard, but if you're just curious, like I am, what happens if we do this? Even if we take p-value of 0.01, we're saying that the null hypothesis is not rejected. Okay. Let's do the same thing for the total solids. Now that's not just the stuff that stays in the water. It's just everything that gets washed in the storm. All right. We got an outlier on the first one, so the pre-examination, and on the post-examine, or I guess it's not post, it's, there's got to be a word for that. Pre, post, and something. Obviously, the numbers are wonky, like we were talking about. Let's see. So this one, yeah, that's in. I can't even draw a box around it. The outlier, so the crazy amount of solids that was found during the pre-examination, it's not even an outlier in the during examination. It's like right here. So obviously very different. The range from the during goes from 0-ish. That's not the important part. The important part's the high one, to 5,000-ish. And the high part here is 600-ish. So it's, the high part is almost 10 times greater. So just from looking at this, you'd say, holy cow, that's bananas. That's way too much stuff. You guys are adding way too much. But your eyes can deceive you. Visually, it's hard to tell. Additionally, even if that is the case, even if your interpretation of this is too much parts in the water is correct, if you just go to them and say, hey, look, here's the data, I'm saying this is too much. If you didn't run a test on it, you might end up regretting making a definitive statement. So we're going to run the same test. The Mann-Whitney, which is a non-parametric, says that we're rejecting this. We got a p-value, or we got a rejection of 0.042. So we just barely rejected it. But we're rejecting the null hypothesis that this is from the same distribution. And we use the other test too. Note that these sets are not paired. And again, we reject. This one is 0.08. So both these tests indicate that the data derived from the distributions with different measures. So meaning that they're probably not the same, not similar to this, in that even though the amount of water coming in, as in it rained more often, they're still from the same distribution. It's not like I went to a entirely different spot to measure. This is the same distribution. We kept the null hypothesis, but here we rejected both tests. Now we can talk about, so the test we just ran was talking about central tendency, meaning we're comparing, where does the central tendency lie, one versus the other. And since we're saying these are probably different, then they probably aren't very close. The next one we're talking about is normalcy. How normal are these distributions? We're going to test the null hypothesis that the sample comes from a normal distribution. Now, I don't think we use this specific one. I think we used the Shapiro one before, but they're similar enough. This particular test combines skew and kurtosis to produce an omnibus test of normality. Omnibus, best way I can explain it is put a lot of things into one go. I do get a warning here because I think our sample size is 17 and it wants 20 or more, but it's just a warning. Okay, so the normalcy test on the total amount of solids beforehand is probably not normal. And the normalcy test on the total solids during is also probably not normal. And they were rejected pretty strongly. So that is the total solids. Okay, I don't see. Let's see what would happen. I think it was TSS. Let's see what happens if we do this for the TSS. Same result. Okay. The next question was, are the data homoscedastic? Which sort of requires us to look up the meaning of homoscedastic. It refers to the variance of the two data samples. Are the variances close enough? From box plots, we see some differences, but here we're asking if the differences are statistically significant. Now that's an important word, statistically significant. Oftentimes, when you're looking for a conclusion on something, you'll find something that supports the conclusion, I don't know, you're looking for, even though it's a kind of a bad way to go about things. But you don't have enough data for it to be statistically significant. So let us try looking at these here. So this says that for the, this is two different tests for homoscedasticity, I guess. And the first test says that it rejects the null, where the null is saying that it is probably homoscedastic. And the second test, the Levine test, does not reject the null. Interesting. So, little description here. The first test we're using is called the Bartlett's test, and it tests the null hypothesis that all input samples are from populations with equal variances. For samples from significantly non-normal populations, Levine's test is more robust. Now, think about what we were looking at before. And as Dr. Cleveland's posting in the chat, are some articles on these topics. But as you see right here, significantly non-normal populations, you should probably be using this one more. Were our populations normal? Well, it didn't look like it. So probably not normal for the pre and probably not normal for the during. So the assumption of homoscedasticity, that's hard to say, is central to linear regression models. It describes a situation in which the noise is the same across all values of independent variables. Heteroscedasticity is present when the size of the error differs across values of an independent variable. Yeah, noise is a I don't even know if you guys are going to have a lesson on linear regression, but noise can really interfere with what you're wanting to do. Okay. Let us answer that question. are the two variances the same? Well, thankfully, we have, at least I think Describe has some of that stuff. No, it's not there.
Yes, it is.
But the closer, what I meant to say is the standard deviation and the variance are intricately linked. So let's look at this one. Dot describe. Oops. Well, I guess I can't say it's an oops. It's just that we need that. There. Okay. So our first test here was saying that they're heteroscedastic, meaning probably not homoscedastic. Let's look at the standard deviation on both of them. I believe them. Oh, somebody must have left. So the standard deviation on the first one is 7,104. Now this is, I probably should have swapped these, but it's just the order it came in. This is the data measured on total solids during the construction. And the second one we have is the total solids measured before construction. Now consider again that the plot here would be nice to. What we're interested in is the variance of what's going on here. And just because the my box out again. So the range that we have here is way different than the range we have here. But for the if you ignore the actual number of what the range is, you can still talk about the variance of this one compared to the variance of that one. So if we go back down here and look, we've described, in fact, I'll just do pre and during. That way it's in the correct order. All right. Oops, what did I do wrong? Oh, of course. Use the wrong data frame. Okay. So if we look at the standard deviation for the pre-measurement, we're getting 361. And the standard deviation for the the during measurement is 7,104. Now, how different are these from the mean? Is a question we could look at. They look pretty different to me. But again, me just eyeballing it and say, these kind of look different, isn't really as reliable as using our tests. So with the Levine test, we do not reject the null hypothesis that these are homoscedastic. But we do have contradictory results. As I was saying before, choosing the right test can be difficult. And one of the best ways to do it is to look at the assumptions for what your tests have. And if you can go with the strictest one, let me say that a different way. The strictest test you can apply to your data will probably be the most accurate. So the Levine test is better for non-normal populations. And since we already discovered that these are both probably not normal, strongly so, we would favor the results given by the Levine test. So Dr. Cleveland just said, to normalize, use the coefficient of variation. It's defined as the ratio of the standard deviation to the mean. Oh, okay. So then, I wonder if you can index into these things. Let's see. I think it's just this. Yeah. This. .st. Okay. And we want that. Which one is it? It's the ratio. Probably the other way around. Okay. So what did I just do here? Well, I took the knowledge he was just talking about. And I'm going to take the mean, and I'm going to divide it by the standard deviation. Okay. So see these ratios. Now keep in mind this ratio is, and I could easily swap it if we feel this. So we're taking the mean over the standard deviation. And for one, we get a value of 1.28. For the other, we get 0.49. Now, considering these are ratios, meaning that it doesn't matter if the data on one is in the tens of thousands and the data on another is in the tens. The ratios don't particularly care of the magnitude of those values, so we can still compare them. And well, these are pretty different. It's not negative, but the one's on almost a complete other side of 1. So this is 0.28 on the higher side of 1, and this is 0.51 on the lower side of 1. So these are almost 1 apart. Take the difference of the two. I wasn't expecting to have to do math. So gotta take one from there. I have a calculator. We're smarter than this. We can do programming stuff. Ratio 1. Ratio 2. Print. Oops, I didn't write it. Yeah, the difference between the two is larger than one of them. So, okay. I don't believe I'm going to have time to look at example 2. But we did at least talk about solving the questions we were looking at. So to recap, for example 1, and apologies for a lot of this lab was a little nitty-gritty. You don't particularly need to know exactly how these tests work. What you do need to know is what code do I need to copy and paste? Which test do I need to apply? And given that test, did it reject or fail to reject? What were we looking at as the null hypothesis? So let's look at some of the questions we were looking at. Are the data approximately normal? No, our test said, both of them said it's probably not. Are the data homoscedastic? No, probably not, because we had 2 tests for homoscedasticity. Tough word. But Which test is more appropriate? Well, one is better for normal. Well, I can't say that. One is better for non-normal. We do know that. And our data is non-normal. So we say no. Do the two construction phases represent approximately the same rainfall conditions? Yes, based on the Mann-Whitney test we ran. Now there's more to do. I'm not sure what the approach is going to be if we're going to continue this on Thursday. I will let you know as soon as I do. Okay, let's see, question. Oh, it was already answered by Dr. Cleveland. All right. Well, I went a little long. Sorry about that. Hopefully I didn't bore everybody. I was trying to give as much real world emphasis on why these things are important as I could. But we are doing p-tests. And when you're doing tests, sometimes it's just technical. There's I can only flavor it so much. So it is 10:53. I'm happy to stay around and take questions, but I do believe we're officially at time. So the recording will be up on.
Yep, we're about to end. I just put a message in the chat
Yep.
box. And that was a good presentation of comparison testing. The last piece of advice is in the chat box is when you can, plot things, because that will help you interpret the meaning of the tests. If things plot on top of each other, and sometimes you don't have to think about the test, you still do it, but it'll guide you onto whether the test is telling you if they're the same or they're different. So that's all for today. Thank you very much for your attention. And this lab is its own homework. So read through the other examples, run them as you can. I believe there's a set of questions at the bottom, and that is the homework for this lab. So bye-bye, everybody, and have a great day.
Thank you.